Hello, I'm nigelargriffiths. In this video we'll be looking at nmonchart. Now nmon stands for Nigel's Performance Monitor. I'm the guy who wrote it. Many of you have probably tried using nmon live, looking at the computer, what it's actually doing now, to investigate some problem or other, or see if there's some opportunities for tuning AIX. This has been part of AIX for 9 years, so you'll always find it on the disk now. The alternative is nmon for Linux. I'm still in control of this one, and it's open source. As you can see, it comes in lovely colors now to help you see how the data is related on the screen. But many people actually want to collect the nmon data to analyze later on. The graphs actually let your brain find trends and interesting things and peaks in the data. Your brain's actually pretty good at doing that if it's seeing a graph rather than lots and lots of numbers. People use various tools to generate the performance graphs. Historically, the Microsoft Excel-based nmon analyzer is the most popular one. When I support nmon users, particularly when they're using the analyzer, I see the same issues repeatedly. First of all, the analyzer takes quite a lot of manpower, and it actually takes them quite a lot of time to generate the graphs. Imagine you have 30 machines and 10 virtual machines on each. That's 300 files you have to deal with every single day. We can batch up some of those operations, but it still requires manpower on your laptop or PC or whatever running Windows. The analyzer can't deal with enormous nmon files. I repeatedly have arguments with people trying to collect tens of thousands of snapshots of data. The analyzer will crash when the files get too big. Nor can you see those on your screen. There's no point in having 10,000 data points when your screen only has 1,500 pixels across the screen. You just can't see all that data. The analyzer is also not perfect due to Excel limits and bugs. One particular nasty one is every time it's updated it's not backward compatible, and some of the scripts then break, and all sorts of mayhem comes out that way. For the newbies, if they get stuck with an analyzer problem, then they're going to give up. They're not going to sit there analyzing the analyzer to try and work around bugs and failures. We also have the Linux guys. They hate Excel. Well, they want to do everything on Linux, quite naturally. I can understand that. Unfortunately, the OpenOffice and the LibreOffice are not up to the job of handling the Visual Basic equivalent. It's just too slow, like an order of magnitude too slow. So we wanted something to be web-enabled, something so that you could see it on your tablets and smartphones as well as your laptop. Keep it nice and simple. We actually want to generate the graphs or format the data on our Unix or Linux machines. Do it all on the web rather than pulling it to a Windows PC. So I looked around for suitable ways of generating nice looking graphs, and I came across Google Chart. This allows you to embed little graphs and graphics in your websites. So I looked at the sample graphs on the Google Chart website, and there's some very interesting graphs, histograms, bar charts, area graphs and bubble charts. I thought these would look really nice, so we could use them. So you're going to generate a HTML file. It pulls in the Google library that's out on the internet. You create some JavaScript data. It's just an array, a comma-separated array of data. You then call into that Google Chart library when you want a particular graph drawn, and it's the user's web browser that actually does the graphing when they click on the button and actually want to see the graph. The format of the data is pretty simple, and it's a natural fit for the way it's saved in the nmon file. Also, Google Chart itself is improving drastically, including getting faster. So what is nmonchart actually in practice? Well, it's around 1,000 lines of Corn shell script generating HTML and JavaScript calls. You run it like just a command. You give it the nmon file and you give it the output file name. And it takes about a second to run on reasonable size nmon files, by which I mean under 800 snapshots, for example. If you got a couple of thousand, then it will take a bit longer to run, but it will just run through it all. So how are the graphs made? Well, they're done by your browser, typically sub-second on reasonable size files. If you've got very big files, then they do take a couple of seconds to generate the graphs. You load them into your browser, either via a web server, and you could put the output file straight onto your website, or you could just double click on a local file and that throws up a browser and you can see it that way. How many graphs are there? Well, there's 53 of them, but it depends on your nmon data file content. So if you don't have user-defined disk groups, then there's a bunch of graphs that won't appear. If you don't have top process data, well then those graphs won't appear. And there are some differences in case of AIX and Linux, for example. The memory stats are completely different, so there's different sets of graphs for either of the operating systems. I've done lots of testing with the script over the past year and before it was even released, but it's been out a while now. So the script works on Power, x86 and ARM. It works very nicely on my Raspberry Pi 2, for example. It works out by itself the differences between Unix and Linux. The echo command and the sort command are different, and awk actually gives you back data in a different order. We also tested it against hundreds and hundreds of nmon files from AIX and Linux, many different operating systems and different nmon generations, and some dating back years. There are some nmon files that we just can't support. The data isn't there or it's wrong, and you'll get an error message if we detect those. Also, JavaScript is pretty unforgiving. What you have there is if you have something in your file that the script doesn't understand, then when you click on a graph button, nothing will happen. You should send me the nmon file and I'll try and work out what's wrong. Well, that's enough waffle for me. We're going to go off to the nmon SourceForge net page to see where you can download it and see some more information. Then we'll actually run the script and we could look at the graphs. The graphs are really nice. Okay, here's the nmon for Linux website, nmon.sourceforge.net, and you can see what it looks like on the screen again. In here, lots of screenshots and things, lots of binary downloads. Of course, the nmon for AIX is part of the operating system, so you don't download that. It's just there when you install AIX. On the binaries, you can see it's been compiled for hundreds and hundreds of. These are the Intel and AMD. Here's the mainframe. Here's the power, and here's the ARM processor reason for the Raspberry Pi. Lots of information and documentation in here. If you can't find the version you want the very latest, you can download it at the current point in time. 16D is the latest version, and we can get older versions down in here if you really need them. And down in here we have nmonchart, and I'd better cover this. We've got Topaz chart as well. You can generate nmon-like data from the Topaz rec command or recording command on AIX, and you have to put it through the parser to generate the comma separated values files. Now the guys who did this didn't quite get the nmon data right, so nmonchart doesn't work, but we had a couple of big banks who had thousands of Topaz recording files that they couldn't graph, so I cut a special version of nmonchart that understands the Topaz format, and they got some other bits and pieces in there, so you can use that. But we're looking at nmonchart in here. And so we have a little example of how to actually use it. Here's the latest release. You click on here, you wait 5 seconds and it will download. It's only a few tens of K in size, and there's a sample file and some other things that might be useful. If we go down in here, we'll see some older versions. We have a gallery of all the graphs in here, one of everything. We're going to show you these live. If you find one, you say, well, what is that exactly? We can click on it and you get a nice big version. Disk percentage, time busy, unstacked, and you can see 100% in here. You got 1, 2, 3, 4 graphs over 70, or 4 disks over 70% busy. Boy, does this machine need some help. If you click on further down, you'll see all those graphs in here. We've got a sort of readme. A comment in here that the nmonchart file is about 20% of the size of an nmon file. And we have a list of all the graphs in here that you can expect to see. If you don't find something, let me know. If the data is in the nmon file, of course. Don't forget, nmon files, you can actually go and edit them. They're just text files, and go and see if you can find the data. One thing we don't cover is more than 150 disks. That is too large a number anyway. If you've got 150 disks, the graphs look absolute mess, and you can't really find which disk is which when you find one that's busy. The way to work around that is for the user to find disk groups. That can be particularly useful to find your groups, your disks in groups of what they're doing, and then you can monitor them as a group. If you're using the Linux, you can use the -G auto, and it will actually remove all those partition stats, which are a bit annoying in the Linux data. Right, now let's go and have a look at actually running it. So I've moved to my development machine. It's called Blue. Big Blue, makes sense. This is me, NAG. I've got a little file that I took at random from my selection of hundreds. I just renamed it to Test to Protect the Innocent, and it's there we are, half a megabyte or 2/3 of a megabyte. The ZZ lines tell you how many snapshots you got. There's one of those for each snapshot, so we got 288 snapshots in this file, April from last year. And I can use timex just to give me how long it took to run it. Here's my nmonchart script, the test file in nmon, and the out file, same thing, .html at the end. And I'll just run that. Okay, 0.8 of a second. Not bad. So I've used the website to actually get access to this file. Down the bottom there's a few things I tend to notice fairly early on. You see it's a Power 7 machine, it's an MMB, so it's fairly old, 770, 780. Here it says AIX Technology Level 3. Whoa, that's a bit out of date. We're on Technology Level 9, it's 6 levels back. Tut, that's terrible. 64-bit, 1.3 gigahertz. Okay, we've got 8 CPUs online, but we're only entitled to 5.5. A lot of memory, 163 gigabytes of memory. Okay, and up in here then we can see all the buttons. I zoomed out slightly to get the buttons to tidy up at the top in here, and so we just click on a button to see a graph. There we go. So here you can see auto scaling of the graphs in here by Google Charts. So it's cut off some at the bottom, so it's not as bad as it looks. And the time and date things are automatically generated, and it does a very good job of putting up sensible things. This could be 30 days of a capture or 30 seconds of a capture along the bottom. You see little grey lines, you saw those in the options, and if I go over things you can actually see, rather than trying to work out what that value is at the top, you can see the 7.555 physical CPU was actually used. Not actually hitting the top of the virtual processor count, that's good. If we look at the next one in here, we have the pool idle. Oh, there's plenty of CPU time available in here. 7 CPUs are always available. There was a little dip there. It went down to just the one. Okay. So that's useful information already. We want to look at the utilization. Don't favour utilization when we got physical CPU stats on a shared processor these days. But we want to look at the ratio in here, the system time to the wait time. And that looks quite healthy. And we're not getting up to the 100 at the top, so that's good. CPU use, classic, isn't it here? 1, 2, 3, 4, 5, 6, 7, 8 CPUs. Oh yes, it's 8 here. For some reason I was thinking 7. And you see a classic, the first thread being used a lot, the second thread being used a little bit, and these little threads up in here not really being used at all. So this is definitely SMT4, we can actually see that down here. But it's only really using the main thread on each of the cores. We could add a lot more work to this virtual machine. The response time might go down a little bit, but the throughput would go up quite a lot. Okay, we look at the run queue. Here we can see the run queues coming up to the peak here at 13. But you can see a lot of the time it's down here at the 7, so it's only using the first thread. We could throw a lot more at this. Process switches tend to be horrific numbers. You can see the top one up in here. 30,000 switches between processes a second. It's amazing how fast our CPUs go. When I started off, that would be in the hundreds, but now we're into the 30,000 area. System calls. This is calling the operating system to do some work. We can pick it in here. Get grief. 393,000 times it's asked the operating system to do typically reading and writing type operations onto the disks and networks. This is fairly healthy. We've got the read and writes at the bottom, and we can see a sort of mixed ratio between the two of those. Right, the read and writes, it's good to have a look at the mixture in here. Some peaks in the reads, and the writes steadily going along. This actually looks like a sort of database class workload. Okay, fork and exec, we can see 40 processes a second being started off. That's quite high, depends on the workload a lot, but that's quite a lot. I'd be worried about some people running shells in loops to actually gather data and things. Real memory in here, so we can see the real free in blue. This is the bit in use in here, and this is the bit that's always free. We've got spare RAM in here, so we've got 12 gigabytes of unused memory. There's a tuning opportunity. Virtual memory. Yep, we are never running out of virtual memory. So that's fine. File system cache. Yep, the file system cache coming up nice, the num_perm value. So we're not using a direct I/O or concurrent I/O. We're using the file system to reduce the amount of I/O we're doing. Classic use. I hope the operators are expecting that. Paging. Oh, tiny burst right at the start. But 0 all the way across. That can be an nmon collection issue. That the first one is always difficult to collect because you can't compare, can't get a delta. Here we go. Oh, this is an SAS workload in here, and this guy is taking the most CPU seconds, and it's doing the most I/O. And the size in here is how much memory it is. It's enormous. Typical operation of SAS, actually, that I've seen in the past. Everything else is down here. The whole operating system and lots of daemons. Not a lot in there. Okay. We look at the CPU by command in here. Again, we can see that SAS is the dominant one. There's a few little workloads coming in and out in here. Bright red SQL LDR is operating. Okay, networks. This is the one that I always like. I think it's beautiful. The read is on the top and the write's at the bottom. We can see at these peaks in here, all the data coming in is immediately going out to the machine. So it's like transferring data through itself. Generally, there's a little bit more reading than writing at other times. But this is only from 3 o'clock to 4 o'clock, so it's only an hour of the workload of the day. Number of packets, we can see that coming and going. Oh, it jumps up at this point. Lots more data actually being thrown out. The network sizes, again, that comes and goes. Definitely two sorts of maybe data packets and user packets coming in to very different sizes. Adapter stats, very peaky. So a lot of the data is being captured in that file system cache. Typically, though, if it was more of a database workload, then we just want to make sure that all the adapters are doing some work. We're not doing it all on one adapter and the other one's just hanging by. Let's look at our disks. That took a little while. You see the list of disks in here. There's a lot of them. There's 9 more of them. I can click down here and see them all. Unfortunately, the colours are sufficiently overlapping that my poor old eyes can't distinguish between these sort of colours in here. Slightly lighter, this one. And this is why we don't like to go over more than 60, 70 disks or so. But in here we can see the disk busies. This is stacked. So if we go to the next one, the U is the unstacked. There we can see the 100% at the top. Oh yes, we've got some disks running at 90% up in here. We can't determine, this list isn't long enough to determine which they are, but there's quite a group of disks running at 90% busy. We should get that fixed. That will speed up the operation of the machine. On the read, again, let's look at the unstacked version. So we're going to, can't see it, 120 at this peak in here. If we go 120,000, if we go to the right unstacked, yep, the right unstacked is much, much bigger. So we're doing mostly writing here. Can we catch one of these big ones? Nope, we can't. We catch this one. Nope. Okay. I selected this one to have a look at, mostly because we have the disk service times in here. So if we look at the disk service time, quite a lot of disks. That took a little fraction of a time to display that. So the service time, oh, that's quite big, isn't it, in milliseconds? So that took a whole second for that operation there, and the same in this one in here. If we look at the read service times, yep, those two same points. If we look at the write service times, then they should be not the same things. There we go. So the right one, or much less. So we're writing very quickly. There's occasional packets coming in from the disk that are taking over a second to arrive. Should look at that. Maybe There's only once or twice. Maybe the SAN is being overworked. We have the disk wait time here. Again, it's the same point. I think there's quite a bit of wait queued up, not actually being sent out to the adapter yet, for that to come back. Although it's only 30 milliseconds, that's not the whole thing responsible for getting the data back. At the end in here we have journal file system stats. Again, they've got a lot of file systems online here, and we can see some of them up here going up and down as we move across. It doesn't help very much, does it, with too many things in a key. Typically we can see things here. We can see the one here slowly ramping up over time. If this was up the top in here, then we could see it going to hit the 100%. Maybe we'd actually have to do something about it. The IPC, the inter-process communication, these are the semaphores and messages. We can't show shared memory access because that's done at memory speeds and there's no stats involved. But we can see here that we're doing 300 semaphore operations a second. If you understand how the application is written, you may want to. That may actually help out. You can see the messages aren't being used at all in this case. Okay, so we can very quickly have a good view of what's going on in here. It took us a second to generate this, a second to show it, and when we're actually clicking buttons in here, apart from the disks, there's so many, these actually come up very quickly so we can quickly scan through. I'm using a tab browser in here, so I could have a different machine in each tab and quickly go through them all, compare machines. Is the database server peaking at the same time as the application server, and that sort of operation. Well, that's it for nmonchart. Ongoing development, lots of new releases coming out. Keep an eye out. If you have a really good idea, please let me know. Sometimes the easiest ideas can be very simple to implement. As it's quite fast and you come up with a new graph or a new way of looking at something, you can go back and regenerate all your data and get the new graph for everything. It's just corn shell. It's quite big, but it's quite simple to understand. I've even commented it. If you hack it, can you send me a before and after copy? Then it's easier for me to spot the differences and where you've changed things. It may be possible in the future that we can actually live graph data as nmon's generating it on the fly. We'll have to think about that one a bit. Most of all, have fun. And if you like this video, then please click the thumbs up button below.